Hi, in this video we're going to show you how to solve some equations with exponentials and logs. By now you should have been working with exponentials and logs quite a bit. If you haven't seen the other videos, please watch those first. And this is kind of a conclusion video where I'm just going to throw some equations at you there and we'll discuss strategies on how to solve them. Okay? So the first thing in the strategy for solving is that this is called solving exponentials and logs. So the first thing that you're going to want to do is you're going to isolate the exponential or logarithmic term that you need to solve out. Okay, so really we're going to consider that we're in two different types of cases here. Either we have x inside a logarithm, that's one of the cases, or we have x inside an exponent. Okay, so either way, the very first strategy that you're going to implement is to isolate that logarithmic term if the x is inside a logarithm, or the exponential term if x is inside an exponent. Okay, let me give you an example of each of these cases so that you can see how we would do that step one in either case. Let's say on this side I have this equation, negative log base 3 of x plus 2 is 1. Over here I have a completely separate equation, 600 is equal to 400, 1 plus 12 over 400 to the 4x. Okay, so take a look at these two equations. Would you know how to solve them by this point? If you want, you could just pause the video and try to work these out and see where you're at for solving these types of equations. Alright, you can see that over here we have a logarithmic term, and that's the term that we wish to isolate if we're going to do step one, which is isolate it, because the unknown variable x is inside the log. Okay, so for that we would want to multiply both sides of the equation by -1 to get rid of that, or any other multiplicative term over here, you'd want to get rid of it first. Same thing over here, we're going to try and underline the term that we want to isolate. In this case, our unknown variable x is up inside this exponent, and so what you want to do is consider what is the base that has the x inside its exponent. And you see that the base of this exponential function here is this quantity, 1 plus 12 over 400. And then this number 400 over here, that is not part of the base. That is not raised to 4x. So in order to isolate this term here, we're going to divide both sides of the equation by 400. Okay, so that's what I mean by isolate that term. And then step two is, let's say if the x is in a log, what you're going to do is raise both sides of the equation to the base. Okay? Or sorry, you're going to, what you're really doing here is you're actually, let's say like here, we're in log base 3, right? What we're going to be doing is actually exponentiating both sides of the equation, 3 to the power of the equation. Okay, so that's really what I want to say here. If x is inside of a log, then you're exponentiating the equation, both sides, using the base that you're in. Okay, so this is specific here in this example to base 3. If this said ln, then that would be specific to base e, etc. And then you take that base and you raise it to the power of the equation. And then the other case is if the x is in an exponent, and then what you're going to do there is take the ln of both sides. Now, some people will say, why don't I take the base that I'm in to both sides, take the log base whatever. You can also do that. That's an alternative method. But this way is a little bit easier because, as you saw in the previous one, we had the change of base formula, and that's generally used to relate everything back to base e, the natural log. So if you do have x inside an exponent, you could take the log base of whatever this quantity is, or you can just take the ln of both sides. So you'll see me enact that way where I just take the ln of both sides. Okay, so let's use this strategy for solving here on each one of these. And step one, the first case, is that we need to isolate. Okay, so I'm going to isolate this term that I've underlined in red by multiplying both sides by -1. And then I go on to step 2 here, and I'm in this top one where x is inside a log, I'm going to exponentiate both sides using the base. Okay, so keep in mind that if you're in this type of case, it is base specific. So if it's in base 3, you're raising 3 to the power of log base 3x plus 2 on that side, and you're raising 3 to the power of minus 1, because there's minus 1 on that side. Okay, so that's what I mean by that. And the reason that you want to do that, if you recall, a to the x and log base a are inverses of each other. Okay, so we're going to use that fact to cancel the operation of raising 3 to the something with the operation of taking the logarithm base 3 of that thing. And what's going to happen is when these two things cancel out, you end up getting the quantity that was inside the logarithm. Okay, so whatever's enclosed in the parentheses of the log is what you get after you cancel that out using the inverse function. Okay, so on this side of the equation, you're simply left with x plus 2, and on that side, you already had it. It was 3 to the minus 1, or if you want to rewrite that, 1/3. Okay, and then you just solve as usual, because now you've freed the x from being inside of a log, and so x is going to be 1/3 minus 2, or if I want to approximate that to 2 decimal places, negative 1.67, okay, negative 5/3. Okay, so that's how you solve that type of equation. And then if you're wondering if you got it right, you might want to try this on your own. Take the value that you have right here, and then replace it right here for the x, and then take the negative log base 3 of that quantity, and it should come out to 1. Okay, so I'll leave that for you guys to check. And let's go on to this next one. Remember, step 1 of the strategy is to isolate the term. Okay, in this case, it's going to be an exponential term, and we're going to divide both sides by 400. Okay, so 600 divided by 400 is the same as 3 over 2. So that's how I got the 3 over 2, 600 over 400. And then on the other side, I just have this quantity raised to the 4x. Now you may be wondering, why did I give you such a funny example where inside of here I have a calculatable quantity 1 plus 12 over 400. This is to just give you some familiarity and practice with the types of equations that you're going to see in the coming chapter on financial mathematics. One of the most common formulas from financial mathematics is called the general compounding formula. And that formula leads you to end up with funny looking bases like that. So I just threw it in there as a precursor to that so you can get prepared. So that means that if I do see something like this, I don't want to work with it that way. I'm going to want to actually write down what that is as a decimal, and actually I'll just do that on that same step. 1 plus 12 over 400 is 1.03. Okay, so that's another thing I just have to do is simplify that part. And that's all in step 1, where I've isolated it, where I just have a single base to a single power, and that power involves the unknown variable x there. And then over here it says if it's locked inside an exponent, then you need to take the natural log of both sides. In case you're wondering, you could also take the log base 1.03 of both sides if you want. But I'm just going to work with the natural log. Okay, so then on this side, natural log of 3 over 2. And on this side, we get 4x times the natural log of 1.03. Okay, do you know why I have a 4x in front now? I hope that you do, and if you don't, you got to rewatch the video on logarithm rules, because one of the logarithm rules is that the log of x of a to the x is equal to the x comes out front and then log of a. Okay, so that's the thing I'm working with right here, is that it's this number to that number. So when I take the natural logarithm, this exponent part comes right out in front, and then you just get the logarithm of the base just like that. And it's really nice. That's the whole reason we actually did it, is because logarithms have that great rule that allows the unknown variable to become untrapped from the exponent and then put down in front. And so all we have to do is divide everything on this side. We'll say x equals, and we'll take this log of 3/2, and we'll divide that out by the 4, that was right here, and by the ln of 1.03, that was over there. Okay, so that's what I would call the exact value for the answer of x in that case, but you'd probably want to calculate that out to approximate it, and that's equal to 3.43 to 2 decimal places. And once again, if we want to know if we got this right, let's say on a quiz or test, you just take this value and replace it for the x right there, and then go through all that calculation and make sure that it comes out to 600. Okay, so you can very much check your work on these types of problems, and hopefully you feel more comfortable solving them now. Okay, so next thing I'm going to do is go into some applications of why we need to solve equations with exponentials and logs. And here you'll actually get to see what I was just talking about, which is the general compounding formula for compound interest. Okay? So, for example, let's say that we have a 4.8% annual percentage yield account, and it's compounded quarterly. Okay, so I'm abbreviating compounded quarterly by CompQuart there. And the future value on that account. Now when we get to the chapter on financial math, I'll have you derive stuff like this. But for now, I'll give it to you. The future value, how much your account will be worth after a certain number of years, is going to be equal to the principal, that's the initial amount that you put in the account, then 1 plus 0.048, and you may notice that's the same thing as this percent as a decimal, divided by 4, and then raised to the 4t. And that number 4 that goes there and also up there has to do with the fact that it's compounded quarterly. Okay? Anyway, we have this fabulous equation that tells us how much our money will be worth at any given time, at any number of years. And my question is, how long does it take me to double my money? To double my money. Okay, this is a very common question inside of an account. Well, if I put in $100, how long is it going to take before that's doubled into 200? And really, you can play with any two amounts of money to answer the question, how long does it take to double? You just have to take your initial amount and then output double of that. Okay, so the easy way to do this, easy way is going to be to just let your principal amount, the amount that you put in, be $1. And then if you want to double your money, then the future value that you're looking to obtain is $2. Okay, so that's how I would do it for double. And if I wanted to do triple, then I would let my principal amount be $1, and my future value be $3, etc. Doesn't really matter as long as the ratio is consistent. And then let's just fill in those values that we've picked out, and you'll see how the resulting equation looks very much like the equations that I was just doing on the board. Okay, so the future value is $2, the initial amount is $1, and then 1 plus 0.48 divided by 4 raised to the 4t. What's the only thing left that I could possibly try to solve for? That's going to be this value of the unknown variable t right here, and that corresponds to time, which is good because just checking that against the question is how long? How long does it take to double? We'll find out as soon as we solve this for t. Okay, so if you want to test yourself, you can pause the video right now and see how far you get on this using the strategy that I just laid out. Okay, and then let's see what you did here. Remember from that strategy that we want to isolate the term. In this case, it's an exponential type of term where, let's see, if we calculate out this base is equivalent to 1.012 to the 4t. And in front of it, we just have a 1. Now, on the other example, you saw me divide both sides by the number out in front here. And I can basically do that, or because it's a 1, really, it just turns into this. And then step 1 of that process is already finished, okay? We've isolated it to say something equals just a single base to a single power. And then the next thing you want to do is take the natural log of both sides. And when you do that, then the exponent will carry down just like that. And then, as you saw me do before, then you just take the top and divide it by all the factors of the unknown variable, just like that. And then it gives you instructions where you can just calculate that out to as many decimals as you like. This is what I call an exact answer, and an approximate answer is 14.53 years to 2 decimal places. And that answers that question. How long would it take you to double your money? About 4.8% in that kind of account, around 14.5 years. Very useful stuff, right? So let's see if you can try another one of these by yourself. Let's see if we had maybe, I'll give you a fresh equation, different one than that. let's say that we have 3.5% and it's compounded continuously. We'll talk more about what these things mean as we move on. But for now, I'll give you the future value equation, which is the principal value times e, the natural number, to the 0.035, that's this number as a decimal, then times t. Okay? Different equation than last time. And how about a little bit of a different question? How long until I triple my investment? Okay? And I would like you to try to set up this equation by yourself and solve it out by yourself. See how far you can get on this just all together. Okay, so I wonder if you were able to set it up. Remember before I said you can use any two amounts of money as long as they're proportionally, the F is 3 times as big as the P because it says triple. So the first initial step is I'm going to let P be $1. That's easiest for me. And then therefore the F would be triple that of $3. And plugging that in, hopefully you came about this equation right there. Okay? And that's an exponential equation where the t is up here in the exponent. So what are we going to do? Make sure that term is isolated, which it is all by itself right here, and then take the natural log of both sides. So then we get the ln of 3 is 0.035t, technically multiplied by the ln of e, but lucky for us this time, that is exactly 1, right? So the natural log of the natural number is equivalent to 1, so you can just leave that off if you like, and then say that t is going to be ln 3 divided by 0.035, and that's approximately, I got 31.39 years. Okay, so at that rate and that type of account, it would take me over 30 years to triple an investment, and that's any investment, any amount that I put in, it's always the same. Okay, let's try one more question, and let's continue to work with this type of equation where we're compounding continuously, but I'm going to change it a little bit. I'm going to say we're having R%. Okay, this time I'm just going to let the rate be arbitrary called R, and you may have noticed that before, whatever number I had as a percent, I divided that by 100, and then I multiplied it by t up there in the future value equation. Okay, so that's what I'm going to replace the future value equation with now, is the exponent is R divided by 100 times t. And my question is going to be, what would the rate have to be if I wanted to double my money in, let's say, 10 years? Okay, so you saw from the last example, when we were compounding quarterly at 4.8%, it took us about 14.5 years to double our money. Now I want to just double it in 10 years. So what rate would we need to double our money in 10 years? In 10 years. So this time it's a little bit different. I've actually given you a value for t, but now you can see over there I have not given you a value for r. Same thing with the last one. I'd be really happy to see you pause the video here and try the setup and the solving and see how far you get. Okay? So let's see what you got for the setup. It says double. So when it does say double over here, I'm going to go back to the thing where I let P be $1 and therefore F is going to be $2. Okay, that's the trick I use on doubling, is that I just use a $1 and $2. And then when I put it in there, I get 2 is equal to 1 times e to the RT divided by 100. There I just combine the R and the T. You don't have to do that necessarily. Did you do anything else there? Oh yeah, that's right. I actually gave you a value for t. It says right there that I'm going to double it in 10 years. So hopefully you realize that for this problem, the t is already given to you as 10. And so that leads us to e to the r divided by 10. Okay, so really we have the equation 2 equals e to the r over 10. And then when we take the natural log of both sides, we get the ln of 2. And here we get r over 10, really times the ln of e. But remember, the ln of e is just 1. So we have that this equation's true. So if we multiply both sides by 10, that's going to equal r. Okay, and remember this time r represents the percentage rate, the annual percentage yield of the account. So this is the exact value for it, but it's not that helpful unless you've memorized the value for ln of 2. So computing that out, we actually get that r is equal to 6.93 to 2 decimal places. And so what that is it's interpreted as a percent, 6.93%. Is that in line with calculations that I've done in the past? Well, when I did quarterly calculation of 4.8%, I got 14 and a half years. 6.9% is greater than 4.8% by a little bit, and 10 years is less than 14 by a little bit. So it does make sense, and I would also encourage you to try to make sense of all the answers you get, just to make sure you got it right. And another thing you could do to check your work, of course, is take this value right here, plug it right into the r right there, and then if you calculate this e term and multiply it by $1, it should spit out $2, okay? So you can always check your work. All right, let's go into one more example as it applies to business. And now I'd like to talk a little bit about the supply and demand theory that we introduced before. When we were working with polynomial equations, we saw supply and demand fitted with linear and quadratic equations. And this time I'm going to take the supply and the demand equations and fit them with exponentials. And then we'll see how now our knowledge of exponentials could be useful. Let's say that, actually let's just start with a demand function first. Let's say the demand for a commodity is given by the equation not D, but the price is equal to 360 times e to the negative 0.06 q. Okay? So do you remember the PQ thing from before? The Q is the quantity demanded, and the P is the price per item at that quantity. So this is just the price of one of those items. And what did we know about the demand curve? Do you remember? Versus the supply curve? Yeah, the demand goes down and the supply goes up. And so when we look at the form of this, if we just want to think about what it will look like, that actually goes back to exponential decay versus exponential growth. You can see that this is a negative up here. Okay, so this is the one where we're in exponential decay, having a base greater than 1 fitted with a negative exponential. It's going to go down like that, and demand goes down. So that makes sense. Okay, let's play with this equation a little bit and make sure you're comfortable with it. Here, let's say that P is in dollars and Q is in number of items. Okay. Here's my first question. What is the price when 20 items are demanded? 20 items are demanded. Okay, I'll say no more. Try to answer this first question on your own. Pause the video. Okay, let's see what you got. What is the price when 20 items are demanded? Remember that Q, the quantity, is represented here by 20. And so we just have to say P is equal to 360 times e to the negative 0.06 times 20. And then we just have to calculate that out. It didn't say to round it to whatever, but let's see what you got. I got the answer 108.43, rounding that to the nearest cents. Okay? That will be the simplest way for me to try to work with this equation, and then I'll go more and more complex as we move along. The simplest way would be to give you a value for Q. The next hardest thing would be to probably give you a value for P and have you solve out for a value for Q. Okay, so let's say when the price is equal to $15, try to answer that. How many are demanded? How many are going to be demanded at that price? Now, oh, did I say $15? Wow, that's really low. Okay, so I would expect to have way more items demanded at the super cheap price of 15 than 20, because when 20 are demanded, the price is 108. I would expect a lot more to be demanded at this price of 15. Go ahead and solve it out and see what you get there. Okay, so hopefully you set it up like this, where you have 15 is equal to 360 e to the negative 0.6 q. Okay, because we're given the price and we need to solve that out. Now remember your strategy is that you're going to isolate just the exponential term. So the first thing you need to do is divide both sides by 360 to get this right here. And then once it is isolated, you'll take the natural log of both sides. And so you get that the ln of that fraction is equal to the exponent, and as we discussed before, times the ln of e, which is just equal to 1. Okay, and so you can see that the value for q, the quantity, is going to be the natural log of 15 over 360 divided out by negative 0.6. Okay, that would be the exact answer, but if you go to your calculator and try to figure that one out, I got about 15.97 or 53. I'm going to round this one to the nearest item because items are probably sold in whole items here, so I would have 53 items. Okay, that's a lot more than the 20 items at that price right there, but it's not tons more. Okay, and that has to do with the exponential form of it. You could plot this function if you were really interested to see how this price demand function works. Go ahead and plot it, and it would be nice to get to see all that. The last thing that I want to show you guys with this is going to be the question of market equilibrium. Okay, let's say that we're choosing to model both our demand and our supply functions with exponential forms now. Okay, and we'll have the demand function as that, and the supply function for the same commodity, let's say, is given by P is equal to 68e to the 0.02x. Okay, what is the market equilibrium quantity? Remember, that was a really important concept from this whole section on supply and demand, is if I have one thing to model supply, another thing to model demand, at some point they're going to meet. And when they meet, they agree with each other. And that means they're agreeing on a price, and that's what we would usually expect out of the market. If you plot these two functions, you're going to see the demand function going down, you're going to see the supply function going up, and they're both going to look like exponential forms in this case, which means they're going to intersect right here exactly once, and this is the mysterious market equilibrium quantity that we're searching for. And then we could also evaluate either of those functions at that quantity to find the market equilibrium price right there. Okay, but this question just asked for market equilibrium quantity. Now go ahead, pause the video, and test yourself. I haven't shown you one exactly like this, but I challenge you to test yourself on your exponential solving skills. Oops, I have a typo. They're both Q's there. Okay, so now go ahead and try to figure that out. Okay, so did you remember that market equilibrium right here means that supply is equal to demand? Hopefully you remembered that, because that's where you need to start. Well, yeah, I just drew this picture on the board. That probably helped you. So your first thought, I would say, is to take this equation right here and set it exactly equal to that equation right there, and then try to solve that out. This has e's on both sides. This is a little bit different than previous ones that I've solved, but actually the strategy really doesn't change all that much. And the strategy number one is going to be to isolate it so that we have a single base, in this case base e, to a single power on one side of the equation. In this case, we're going to have to combine these two e terms, okay? So step one, which is isolating the exponential term. How about I divide both sides by 68 like this? Okay, I'll start out like that to say that's 360 over 68 times e to this. Okay, now how do I get the other exponential term over here so that I have isolated just the single one? What did you do? There's two different things that you could have done probably to correct things. One of which is to divide both sides by this. Divide both sides by the quantity e to the negative 0.06q. Or similarly, you could have multiplied both sides of the equation by e to the positive 0.06q. Okay? Either one of those is correct. I'll show this one on this side of the board. So if you choose to divide by that, then you get 360 over 68 here. And what do you get here? Do you remember this actually goes all the way back to our rules of exponents? If we have, for example, this is like x to the a divided by x to the b. What does that simplify to? X to the a over x to the b? X to the a minus b. Do you remember that rule from so long ago? You actually had to use that right here. So this is going to be e to the 0.02q minus a negative 0.06q. Okay, and altogether that's e to the 0.08q. So what you should have got is e to the 0.08q is equal to 360 over 68. And let me just show you the same thing on this piece of the board in case you went the other way. Another thing that you could have done, let's say at the top stage right here, okay, 68, and then this equals 360 this. Okay, now the very first step is you're going to have to get all of the numbers on one side. So if you have a 68 on this side, 360 on that side, you definitely want to combine those by division as your first step. And I would say be very careful. Make sure that you do not subtract when you're supposed to divide. I've seen that mistake quite many times, and it really, really messes up the entire equation. It doesn't give you a chance to get the answer. So be really careful with your division versus your subtraction. Okay, we have to divide because they're multiplying both sides. The other choice we could have made here, besides dividing by this quantity, is we could have multiplied by the equivalent positive power on both sides. Okay? And why does that work out? That's the other exponent rule, where if I have like x to the a times x to the b, that's x to the a plus b, right? So on this side, we would have 360 over 68, and we would have e to the negative 0.06q plus 0.06q. Okay? And this whole exponent just cancels out and becomes 0. Okay? But it doesn't mean the equation becomes 0. What it means is that conceptually right here, I have e to the 0. And what's e to the 0? What's any number to the 0? It's going to be equal to 1, exactly. So then you just get a 1 right there, and that's why you're left with that same fraction on that side. And then you'll see that if I went this way, and I used the additive rule, just like I did on the other side, that would be 0.06q plus 0.02q, and so that's why I would get e to the 0.08q is equal to 360 over 68. Okay, so either way, I end up saying e to the 0.08q is 360 over 68. And then I'll just erase a little work here. And hopefully you know how to finish out the rest. And as usual, I would encourage you to do so. Hopefully you're not just passively watching these videos. You've got to try it out as you're watching so that you can make sure that you're successful. What did you do on this step right here? Taking the natural log of both sides. That's right. So then the exponent comes down on that side, and we've taken the natural log of both sides on this side. And then we just say that q is equal to the ln of 360 over 68 divided by 0.08. That would be the exact answer. And what I got is that that quantity is approximately 20.83, or if you want to round it up, and the reason I'm rounding here is because I'm in a quantity variable, which most likely needs to be a whole number, so the closest whole number there is 21. So that would be my equilibrium quantity, and then my equilibrium price would be plugging that into one of these equations. They won't be exactly equal when you do 21 on that side and 21 on that side, because the answer wasn't exactly 21, but you'll kind of get an idea of where that equilibrium price will fall. Okay, so I encourage you to try those out, and I've got a couple of those in the worksheets for those who are in my 147 class, and I hope that you're enjoying it.